And we continue.
Начата запись встречи.
We continue after pause. Now it's lecture number 13, pronounce on purpose as usually. I forgot to say hello, my dear students. Sorry, because for me, practically, there is no difference. I'm just continue. For those who just started to watch it after some interruption, in case you have big interruption in time. Hello, my dear students, class number 13. It's a lecture. It's a lecture about manufacturing. And we started after closed die forging. I opened here a lot of pictures on purpose. You see a lot of beautiful pictures, whatever they are. Some of them may mislead you in terms that they give wrong names. Once again, remind you, I propose you to use, in terms of terminology, correct names and so on in English. I propose you to use that book that I'm about to send you, book of Michael Gruber. Modern manufacturing, fundamentals of modern manufacturing. It's called fundamentals, but really it's a huge book. And in case you need some additional information, open it in proper chapter and follow to explanation. In case you don't need additional information, if you think it's enough for you, then save this book. Maybe it will be useful for you once, but I do not propose you to read it. But book is really written good. As we already hear in these pictures, among these pictures, do pay attention once again. Forging may I have not finished that story. Forging may use or not use equipment. Here is the manual process without any equipment, but tool is certainly necessary. Tool may be extremely primitive, like usual hammer in hand of the man, and the same extremely primitive tool we see right now at the bottom picture, but it's already machined. It's machine applied the force, and tool may be a little bit more complicated in their shapes, and depending on what tool you are using, the operations of forging may have that or another names. And plus to this, look at this, it's called cold forging. Cold, it's not a type of operation. Cold, it comes about state of material, whether it was heated up or it was in cold state before forging. And once again, remind you, when it's hot, it's more easy for us. Material has less resistance and it's more ductile, it's more changeable. It's not cracking under the force application. Actually, may cracks also may create different defects, including cracks, including shrinkage, shrinks on the surface, and a lot of different defects, maybe even in hot state. But in cold state, it's resist more, so we need to apply more force, and of course it's not so easy movable through the slots, through the narrow places, so on, so forth. Let's continue about open die forging, people. Open die forging or closed die forging, do forgive me. Closed die forging, it means that you have a dyer, forging dyer. Now, if we're already here, let's see forging dyer photos. Oh, very good picture. Oh, I love it. Maybe it's necessary to save. You see, here is, we'll try to increase it. Is it increasable at all or not? No, that one is picture of real die. It consists of two halves, you see. And where that scheme disappeared, come back, please, we like you. Here is the part you might see inside, and top and bottom die. No, top and bottom halves of the die, half dies. But that is not true. After forging, parts doesn't look like this. Actually, there is something like typical element of any forging that we will see in photos next. It's visible the line of splitting the die, the line of die half separating here is, and it's obvious that part has so-called draft angles in this place. Once again, remind you what is the problem of problem of forgings in comparison to the casting. It's not so simple to remove the part from die. And for this, At least we use with simplified shapes, even the same part. No, I hope you recognize this part. Of course, it's a piston for piston engine. Not a piston, to forgive me, rod which connected between piston hinged to the piston, and it's hinged to the crankshaft in this hole. Do you see the hole here? It's a deliberately simplified shape on purpose in order we may produce it by stamping. By casting, you may produce it with a hole. By stamping, no, not produce by close or stamping. Do forgive me, I use wrong word because in my brains I translated it from our language. By closed die forging, it's not producible with holes, even of such big diameter. You may do something like cavities, which practically repeat the big hole, but it's not completely a hole. And moreover, I already said you that is not true. After the forging process, part looks not like this. I hope you already scared a bit. Forgive me. Like this. Here is you see already clean parts. Practically, do pay attention. They are all symmetrical, no, almost. In most of cases, stamped parts we use forging, closed die forging, for parts which symmetrical in with respect to some plane. Usually, it comes about the plane of largest sizes, largest overall sizes, and it's a plane of die half separating. On the bottom, in the bottom picture, on the right, you see what part looks like immediately after forging. On the left, you see what it's supposed to be. On the right, you see what it really looks like. What is wrong with this part? What happened? No, you do remember what I said. Closed die forging, it's used. It's wrong place. It's not that slide said. Let me to show you first. Closed die forging, it's used two halves of die, one of them, two halves of die, and these two halves in the outer side of pot, they have something like thin slot, which necessary to be filled with metal, excessive metal. Again, before appearing of computers, it was too much difficult to calculate the necessary volume of part. Moreover, it comes about the part which is in state of heat extension. And to calculate completely all the sizes, what they will look like after this heat extension, it was very difficult. And in order, on one hand, to compensate this problem with calculations, because you understand, one matter is scientific calculation somewhere in university, in some scientific institution, and another matter, the engineer who is working in a shop and working already maybe for 30 years. He knows very well all the processes, all the tooling, all the equipment. Again, I forgot to finish the story about tooling and equipment. And he knows very well everything, has great empirical experience, but maybe he already practically does not remember the high mathematics. Maybe. And in this case, he is not able to use some complex techniques of calculating. And in this case, he will use so-called engineering techniques of calculating. It means simplified one, use primitive methods, use some empiric formulas in order, on one hand, to help him to accomplish, to prepare the processes. On other hand, not to overload him or her with some calculations. So do remember about this difference between scientific approaches to studying of something, to calculating of some, even to simulating of some processes, and so-called engineering techniques of calculating. So on one hand, once again, problem of exact calculating of all the volumes of parts, if part is of complicated shape. On other hand, one more problem, how to make this metal, which is not liquid, to squeeze through all the thinner place you need to do. or to squeeze into corners at least. Of course, there are some fillets there, some radii, but material prefer to stay with radii 5, for instance, and you need radii 3. How to make material to squeeze into these places? Quite clear that material first will, while closing the die, it's rather quick process. It's like, and that's it. It's finished. If it comes about mechanical press, uh, if it comes about the hammer, it will be even shorter, and no, it's like dozen of seconds at all. And but hammer may do some efforts, some times may struck the part. And when hydraulic press, it's not so quick, but also it comes about seconds. How to control part in this moment? How to control metal will flow first while setting. It will try to squeeze through more wide places, and instead of fill inner cavities, it will try to escape from die at all, like to fly away to sides. And in order to stop metal in this dreadful intention, on the way of metal, we have a thin place. It's something like bridge. It's called here flash land in this place, da? And flash gutter. Uh, the place which looks like, really, it looks like a bridge between flash gutter, flash receiver, and the part itself. Let's take a look onto another slide. Here is, look at this. In a scheme, it's greatly visible. Where you see hatchet elements, you see the die. Die, it's on the way to be closed, but not closed yet. And to remember what did I say, that in real, it's not closed. Despite it's shown here that it's top half and bottom half, they touch each other. No, they will have some clearance, at least some dozens of millimeter. No, I mean some portion of millimeter clearance will be. Really, it's more than portion of millimeter. And here is, we see the die is about to close. Third one, white one, it's some piece of metal. Maybe it's plate, maybe piece of cylinder, maybe it's piece of billet, whatsoever, doesn't matter. It's not deformed yet. And we would like to make it to fly, to flow, not to fly, sorry, to flow inside of these inner cavities. Despite of our wishes, material start flowing, look like it's flowing aside, it's setting, reducing on height and increasing in width and maybe length, but it's trying to escape from die. It's trying to fill this area first. That is why this area made as a bridge, literally with very thin thickness. As only die about to be closed, material locked inside. Here is very thin place, and moreover, material die is closing far, practically touching this halves. No, not really touching. Doesn't matter. And what happened? Material is already here in this bridge and trying to escape. But when it's already half filled maybe, or filled this flash receiver, but what happened? You do remember this story about solidification of layers which are closer to the casting form, to the die? You do remember. What happened here? Thin place, no, literally less than millimeter. And this thin place, of course, it's already frozen. Die was partially cold. No, it's more cold than hot metal. If even it's hot state forging, die is not so hot. Of course, after forging of some hundreds of parts, it's not cold. Better do not touch such a thing in real life. But it's colder than the part itself. And in this place, because it's thin place, heat transfer extremely intensive, and this place it's already cold comparatively to all another massive of material. And it create metal lock, and it's locking all the another metal inside of die. And die has no another choice actually than to fill all the cavities that intended for filling. So this flash, this piece, on one hand, to compensate our problem with the calculating, if we have such a problem, but the more serious point of this area is to lock metal by this metal lock practically, no? By the thin metal bridge, to lock metal inside the die cavity until we still have not closed completely the die, and to make material to fill all the inner cavities, inner gaps. I hope you understood this explanation. No, I trust you understood. Well, and what do you see right now? You see a scheme of multi-positioning die. What does it mean, multi-position die? Oh, by the word, thanks to this picture, for this picture. Thanks for this picture. May we reduce it? Yes, we may. Oi. Oi. Has disappeared. Do come back to us, please. Oh, you see. Do you remember what did I say? That is not true. And why it's not true? You see it right now in a picture on the left. Here is this connecting rod for piston engine, for piston cylinder. And what do we see here? It passes through some transformations. And this all transformation being fulfilled immediately in the same die, like step by step. First step, second step, third step. No, maybe besides of cutting of flesh, but may happen that even cutting of flesh is fulfilled on the same on the same station. And when we see the video next, not now, next, some more practical class, we understand that the operator of this die, let's say, it's the work of operator is like quick replacement of hot piece of metal. Here, place hot piece of metal after first shaping. It looks like this. It's a redistribution of metal to the places where volume of metal will be greater. Because first it was some piece of bar, piece of cylinder, and of course it was of uniform thicknesses. In order to reach, to fill all the cavities here, we need more metal here in this place. In order to reach all the cavities here, we need less metal in this place. And first step in this case, you see, it's like not even similar to a die at all, this first station in a die. First station was purposed to redistribute material along the axis in order to collect it in the areas where it will be more usable. After the second step, you see what it might looks like. It's already appeared a flash, but seems almost ready, but not quite. Pay attention. On one side, we still miss the piece of material. By the word, not sure that after such dreadful situation, it's possible to finish it finally. No, that is a scheme on purpose for students to understand. And on other hand, you see that not all details in this place and in this place, they correspond to the final appearance, final view of the part. And after you pass it all three stations, like preliminary one, first one, second one, you has got what? As I usually call it, smashed egg by the word. No, it's similar, да? Yolk and the whites. Really looks like smashed eggs, fried eggs in their in your frying pan. This thing should be cut, and this operator, as I said, you transplace from place to place, really by rotating the part. Usually they hold it with special tool and with special tooling, to be correct. And next, it's remove part from die in order to work with the next one and replace it either for cutting die station Or maybe cutting die station, it's like continuation of the same die. No, it was schematic picture. Now let's see the real one. And what do we see? No, there is no 3 steps, but at least we see couple of steps. And in case we'd like to understand which one is final, easy peasy, my dear, let's compare. Where we have more detailed appearance, more detailed view of the part. Certainly on this side. Here is more primitive, and if you pay attention, for instance, to this place, in part it will be a hole. In a part, in this place, what in such place, it will be hole. But this hole is half powered with half poured with the metal. You understand? It's not really a hole. It's like with bridge in the middle, and where the hole is deeper in this place, certainly. Here, hole is not so deep after intruding of this material, after protruding it through the metal. Where hole like in of more complex shape at this place. So that is the final die, that is the preliminary die. No, actually they are combined in the one piece of metal, as you might see, because the sooner, the faster you have next stroke to do until it's yet in hot state, the sooner the better. And really it's just replacing, maybe replacing with rotating if part is so axisymmetrical, maybe more accurate replacing, but very quick replacing from place to place between strokes of hammer. It doesn't depend that it doesn't mean that it depends on time between strokes of hammer. I'm talking only about that we need to replace part quickly in order part, especially when it comes about hot forging, until part is not cooled, and it's cooled even in the air very quickly. And after cooling, it will be already not so ductile and not so appropriate for forging. And how to make the forging die? Here as you see, there are processes of milling, what we are going to talk about next, fuse milling processes, and these milling processes, they create inside of some plates, they create their inner cavities. How may understand it comes about die? No, in particular, what by these holes, those holes on 4 sides. Look, 4 sides, with here is not visible, with holes. No, in another pictures it may be notable, and those holes, they screaming, I am a hole for guiding columns, I am a hole for guiding elements or guiding pins or whatsoever, in order to halves of die coincide exactly 1-to-1. No, what like it's in the scheme. No, in the scheme, of course, it's scheme of process. There is no the place for all detalization of tooling, of equipment, of whatsoever. And let's come back. I hope this time I will finish it. What is 3 groups of devices? Equipment, tools, instruments, and tooling. Look, equipment, I hope you understand. For forging, equipment is either it comes about hammers or manual or machined one, mechanical one, or it's a press, and press may be of different types. It's equipment. It's transform energy, electrical energy of compressed air, whatever energy, maybe it's work on explosion, who knows. And this energy is transformed into linear motion of RAM. And RAM is typically joined to the tool in this process. What is the tool? When we're talking about this forging, closed die forging, what you see like halves of the die, they are tool, they are instrument. And there is one more word, tooling. No, once again, in English, they have no clear, clean, stable terminology. They have, no, in my opinion, and maybe in opinion of other people of my language, they have problems with terminology, and they may call either different things with the same word, or the same thing may be called with different words, and everything is considered correct. Look, they may use word tool and tooling deliberately for everything at all, but let's agree together that we are trying to talk correctly in our courses. Equipment, I already said sometimes. Tool is something that made transformation, some piece or some matter that responsible to make transformation, would physically, chemically make transformation. And in some processes, you can't work without additional things which are necessary, either to direct the part, the workpieces, so called, to direct workpiece with respect to the tool. Let me to show you. Look, this man, nah, it doesn't help me. This man doesn't help me. No, this place may help me. You see these beautiful devices. Yep. And in that place where we have seen a piece of video, we also noticed the man. I trust you noticed it, the man. Where that man disappeared? He left us. Oh, look. Here is the hot pot, and man hold the pot in some auxiliary device. Whatever it's called for, called in English, there is auxiliary device which is not necessary. It's not responsible for providing this process, but man can't hold the pot immediately. What else may be considered like tooling? For instance, some device which direct some elements of die at all, no? Which direct two halves of die with respect to each other. Now, in this scheme is not shown, but I hope you already understood. For correct coincidence of top half and bottom half of die, they have guiding elements. In case these guiding elements, they are not immediately belong to the die, I'm afraid that you are not listening to me right now, but watching the video. Let's stop it. I promise to show you this video, but not right now. If something, it doesn't, no, some elements, like separate elements, which inserted into die, or die is inserted into them, those elements, they are don't take part in transformation if they are no way, no any way touch material at all, whether they improve it or spoil it, doesn't matter. They are tooling. Tooling, no, and what is also not good in English, tooling may be understood also as a process. The process of staffing of manufacturing with equipment, tooling, and tools. No, we do remember next that we have on one hand equipment, on other hand we have tool, and something intermediate, what is not taking part immediately in transformation and not apply energy, but this something intermediate make process possible at all. In terms that either it's direct the tool and the workpiece with respect to each other. We will see examples in another processes. Or it's direct pieces of tool instrument with respect to each other, because tool may consist of couple or more different pieces. However weird it sound now, no, in example of die, you have it already understand, I hope, that tool, one instrument may consist of couples and more elements, which completely necessary to accomplish the process. All of them are necessary. They do not work separately. Next, no, as I already said, tooling is something also that may be responsible for holding the tool at the machine table, or holding the workpiece on the machine table. A lot of functions, and what is one more additional truth? Not all the processes need equipment, tooling, and tools. Of course, quite clear that each process of transformation usually have some tool instrument, but some of them may be accomplished without tooling, and some of them may be accomplished even without machines, without equipment, when it comes about manual processes. And in order to make you to think, I will give you example which I'm not finished. But answer to this example will be in next class, if I'm not forget. Example and ask you a question. What is a tool? What is equipment? And what is tooling in this process? Example is very simple. In kitchen, you are boiling potato. No, it was raw potato. You peeled it, place it to the hot water in the pot, and boiling it, cooking potato in your kitchen. Question is, what is equipment in this process of cooking potato? What is tool in this process of cooking potato? And what is tooling in the process of cooking potato? Right now, I'm not going to answer. Next time, I will try not forget. In case I forget it, more probably you have opportunity to ask me immediately in our so-called open classes when we really have online class, not like record pass it to you. Very well, young gentlemen and young ladies, I trust. Let's continue. Так, what about time? Time we have. Let's continue. Where have we been? Once again, we've been in the process of closet die forging. Whether it's hot or cold, closet die forging, it means that we have tool in the view of die. More probably, we have machine in the view of either hammer or some different types of press. And next, tooling. Tooling may be not present in this process. When it comes about casting, what is the tool in case of casting? Not quite clear, the casting mold is the tool. And do we use any sort of equipment in this casting process? No, casting process, it's multi-stage process, as you have seen. It's for each, practically in all the casting processes, for each repeatable process, they need to pass some little stage of preparation first. In manufacturing process, each time they are forced to prepare the new mold for themselves, because previous one, after a part was removed from this mold, previous one either broken or spoiled. And if we're talking about the equipment for casting, we may say that equipment for casting is furnace, oven. Furnace, oven, something that melting material. If we're talking about the tooling for casting, what we might say? No, once again, to pay your attention to not to these slides. Regularly mixing up where to find the necessary picture for you for illustration. To pay your attention to the picture of pouring metal. Да, while casting. No, quite clear that it's maybe some vessel. No, this one I trust it was it was container in furnace at all. Actually, it's a sort of converter here, but little one, toyish one. And actually, such a thing, if it's not element of furnace itself, such a thing may be considered like tooling for casting. Without this, you will not place this liquid hot metal into your palms and pour its into mold. Yes, you need some auxiliary device that might help you to bring hot metal to the casting form. So casting form, casting mold is a tool. Machine which is responsible to melt metal may be considered like equipment, and in case that is not element of machine immediately, but some tooling that you use to transport and take hot metal to the mold and for pouring the mold, it's maybe considered like tooling. Well, important, not important, but better to understand those things. Well, let's continue. What we continue with? We are already not in the process of bulk deformations. We have already passed casting, primary deformations, forging, both open dia forging and closed dia forging. And now we're talking about one type of deformation. It's called sheet metal stamping. Actually, sheet metal stamping is much more wide concept, much more wide field. It's hidden not only here, transformation of shape. Next, you will see sheet metal stamping operations here in transformation of volume. Why it doesn't move? In transformation of volume, you also will see elements of sheet metal stamping. But now maybe we will talk about all of them, like a bit intertwined, but next we will try to separate them. Why it's not considered like bulk transformation or bulk metal process? Let me to find our Professor Michael Grove. A lot of beautiful things here. I opened it twice in order have opportunity to save as I'm not able to use content. In order to save some pictures that I need. No, like to hold it immediately in front of my eyes. Here is classification that he proposed. And in this classification, we see that sheet metal working is separated, you see, from bulk deformation. And quite the same, it's made in our standards. I will explain you right now the difference. I trust you understand it intuitively. Do pay attention what it's given here, like sheet metal working. Bending, deep or cup drawing, shearing, and miscellaneous processes. No, great. Well, among these miscellaneous processes, we have also mostly deformation processes and some of cutting processes. Shearing process, it's cutting process, so it belongs to the group of transformation of volume. If we separate something or add something without joining, just add something like additive technologies, additive manufacturing, it's considered like transformation of volume where you disappear the book. And bending, drawing, the miscellaneous process, which include, for example, include roll forming or just forming or whatsoever they include. Mostly it comes about deformation processes. Once again, so what is the difference? Primary difference in the kind of workpiece. But in our standard, it's called, if I translate it for you right now, it's called hard scheme processes and soft scheme processes. Where the hard process, where the soft process. Sheet metal, it's so thin, so delicate. Maybe it's soft scheme process. Yes, thin metals like envelopes, like shells. No. Sheet metal working is hard scheme processing. And bulk deformation, which is bulk. No, it's soft scheme processing. Why such separation? Soft scheme processing means it's referred as changing of all three possible sizes in all three directions. And this hard scheme process or hard scheme processes, they are considered like changing of two directions without changing of third one. So sheet metal working, whatever it comes about, either it's cutting or it's some sort of deformation, it's not about to change the thickness of material. And one more time, one more revealing of the dreadful truth. Sheet metal work not only with sheets. Sheet metal working is understood as work with thin walled objects like sheets, no plates somehow. Sheets, next, profiles, especially extruded profiles. Next, pipes, it's all objects of sheet metal working. What about bars and billets? They are considered like workpieces for bulk deformations because they have no thin walls. And while deformation, in case you use deformation, all cross section will be spoiled. No, the length may be changed due to setting processes or extension processes, and the cross section is changed. In sheet metal working, no, like it's supposed to be, thickness is not about to change. But one more revealing, it's changed. In some processes, sheet thickness change. It's vary a bit. And varying, now it's changing. And this varying may be resulted in dreadful situations like tearing off the pieces of sheet metal while deformation. Let's continue. What about time? We yet have time. Do find the necessary place in the slide. Kinds of deformation. Sheet metal processes. Now, here is, you see some different names, some different processes, but this place, it's not separated onto, no, according to our groups of general sequence of transformation. On the top, you see process. On the top, you see two pictures which practically the same, I would say. If you not consider the right side, what is the difference? Difference is, do pay attention. At the top, you see process either of blanking or of punching, it's so-called, and it's cutting process, which called shearing process either. Why shearing process? Because this kind of cutting, it's with no perpendicular to the thickness of material. It's like shear stresses working in this deformation. And this deformation is ultimate. It's resulted in separation of material. So it's shearing process, as it may be called in some literature, or cutting process, as we see on our own. What it will be resulted in? It's resulted in appearing of work pieces which completely flat in cross section, work pieces which repeat the shape of tool. And our task next to understand what is the tool and how to call it. No, in case we still don't know it for some reason. Next, no, once again, problem is these dreadful people may use their English language. No, it's their language, so they use it as they wish. You see, right now it's written die, да? But normally in a book it should be called die block, not a die. But they may call it die, half die, form block, no, but not for this process, form block. They may call it male die, female die instead of die block and punch. Next picture. Do you recognize this word? Drawing, but here it's at least with adjective, deep drawing. Deep drawing is understood as making cup-like parts, hollow-like parts which looks like a cup or some barrel or something like this, and typically they have bottom. But to be frank, also they may have not bottom. And here is, you see, it's called redrawing, да? But really it's still deep drawing. It's not another process. It's still deep drawing, but second step. Why it's necessary, those second step and so on. It's not in your course, but when you, no, those of you who have chosen technology, manufacturing to study more deeply as their specialization in major, they study, in our university at least, they study each semester another group of transformation. Casting, and the whole semester about all the kinds of casting, about the not so shortly and jammed as I did it, да? But a lot of information about kinds of casting, peculiarity of processes, advantages, disadvantages, technological modes, rules of preparation, a lot of different things, including how to design the tooling for casting. The tools, actually, not tooling, but tools. Next, sheet metal stamping separately, machining separately, assembling separately. Moreover, when it comes about additive manufacturing separately, welding separately, the whole semester. Of course, not so quickly, not during 2 weeks, the whole practically half of a year, but also you are studying a lot of processes in details and spend a lot of time for studying different groups of technologies. So we are not explaining here why, what is the difference, this drawing, redrawing. Just trust me on my word. It's the same word, the same process. This one, what is called ironing, it's practically process of forming, what is called forming. And in different books, you might see different names and pay attention. Here is, it's called with different names. It's a drawing, no, so-called deep drawing. It's a deep drawing, but of another diameter and height. It's a deep drawing, yet if it has bottom, it's a deep drawing. If it has no bottom, if it's shown without bottom, it would be so-called flanging or forming, depends on. And that one is also deep drawing, but bottom has another shape. So whatever it's called here, dawning, drawing, so on, it comes about the same process. And this name, dawning, it's also applied to the one of processes of cutting. Oh my poor students, it's not so simple in English to understand it. Well, let's continue. Once again, so sheet metal stamping, it's a group of operations. Let me to show you by the word. Maybe it will be useful for you. I hope it will be useful. Sheet stamping is the group of processes. Until I scroll it, I will stop for a while. It's a group of processes that work with sheet-like workpieces. It means that workpieces preliminary has thin walls, and whether we're shaping or cutting these thin walls, they are not changing. They should not change their thickness. We change only overall sizes of the part we are working with. So the blank for like workpieces, preliminary workpieces for sheet metal stamping, it may be really a sheet. It may be some profile. Usually it comes about extruded profiles. And it may be the pipe, either with thin walls. Very well. And I have noticed that I forgot to show you some things and forgot to say you one important consideration, let's say, about forging. Look, what is more expensive? What that is not final part. It's a forging. You see, couple. Да, by the word. Again, thank you, English language. In English language, result both and process of forging, casting, they are called with the same name. Casting, at least, may be called like castes, casts, pieces that been casted, may be called like casts. But in forging, both process is called forging, and what you have obtained due to the forging process application, it's also called forging. But right now you see forgings, metal pieces made by forging process, which place it on the floor of machining shop. And one more picture, it's machining shop. It means shop of cutting, and already visible that, no, it's another enterprise. It's already visible that something similar to this they are about to produce. They already made some rough preliminary steps for milling. And they are going to produce this complex shape. It looks like the bottom frame, neither here or neither either here or do work. either here or here. It's piece of fuselage frame under the bottom of under the passenger floor. They about to produce the same, but by another technique, by cutting. Again, which girl is better? No, that example I have not explained it to you yet. And maybe I will explain it in real class, I say. Look, what is better? Why do you imagine that here you need approximately they put on backside you see the foot of one of my students. Do compare the size. Approximately the length of this thing is my height. It's more than one half, than meter and half. It's around 80, 65, 87 T, maybe even greater. No, because the diameter of the airplanes been produced in our enterprise, outer diameter was 3 and something like 3.10 meters or 3.1 centimeter, for instance, 3,000, approximately 3,000 millimeters. And that is, no, of course, it's not along the central line, it's lower, as I explained it yesterday. The flow should be lowered with respect to the central line, but whatsoever, it's long enough, and moreover, those pieces they are protruding for holding the landing gear, for joining the landing gear to the fuselage frame. Here, something like brackets in this place with huge holes, fuse, and they are practically 2 meters length. Do imagine what is the size of die you need, consists of two halves, to produce these parts. Let's come back to the picture of die to remind you that die, let's come back to the picture of die, not in the slides, да? Oh, hard life. Do imagine size of the die. Even they are produced individually, in case they are produced individually, not by couples, not for different steps inside of one die. Have imagined the size of die, yes? Do imagine the size of machine, the table of machine, supposed to be, to produce such things. Why so complex? Why we do not cut it like those people? Let's do it like this. Cut piece from immediately from the plate. What is the problem? Problem is answer hidden in another set of slides. Wait a second. Answer is structure, inner texture, inner grain structure. On one case, it's guilty for anisotropy of your part properties. No, seems like in one case, but on one hand. But on other hand, this texture, this inner texture of mechanical engineering parts resulted, and it's tested and proved, it's resulted in higher fatigue strength of these parts. If something you producing by machining, and anyway, this machined piece, it also has texture that left here after the rolling, for instance. You are cutting this texture, like in normal direction. No, do imagine that it was a plate and it has texture along the plate, quite clear. You are cutting the layers of this texture, and it's like does not correspond to the outer surface. Cutting goes perpendicularly through these layers. And in this case, such a part has less fatigue life, less fatigue stresses. It's better work with fatigue stresses. Fatigue stresses, it's repeating fatigue destroying of parts. It's repeated application of loads in different directions, cyclic loads, plus, minus, plus, minus. You do remember maybe that airplane, I hope you already do remember, you already watched it. We talked, I spent the whole class about design for this to show you phenomena of so-called aeroelasticity, and to explain you that airplane really it's not stiff. Altogether, as a whole, it's strength enough, whether it's airplane or it's some missile or helicopter, aircraft, it has enough strength to stand, to withstand the loads applied to the different elements altogether. But locally, it's not so strength. And the worse that it's subjected to, it's affected by different loads in different directions, including this dreadful flutter loads. Why? Uh, you've seen it in a movie on your own. It's a movie, it's not animation. Why pieces of a plane being destroyed immediately in flight due to this flutter? Not even big loads acting there. No, how this flutter self-oscillating, how it's self-supporting itself. I tried to explain you due to the effect of coincidence of inner frequency of your structure, which like appear on some speed. No, you have some inner frequency, no, not you, but structure. It has some frequency of inner oscillations. Let's say each element in this universe has it, and everyone is different. Like it's sounding inside on some frequency, and when happens that outer oscillations in frequency coincide with inner oscillations, it's a period phenomena of resonance and it's quickly destroying the structure. But similar matters may happen. They are not so quick, but they no less dreadful. May happen during some years because structure is not stiff and it's permanently in cyclic way permanently move a bit up, down, up, down. When it comes about fuselage on the ground, inner pressure in passenger cabin correspond to outer pressure. But when you go some height, outer pressure for passengers, it will be not sufficient. No, do you remember stories about Everest climbing? Yeah? People goes to the Everest, crazy people, as for me, do forgive me. They goes in special oxygen masks because it's not enough oxygen on height of 9 kilometers, and airplane fly even higher by hours. And in order passengers survive in flight, we have pressurized cabin, and this pressurized cabin have pressure that correspond to the pressure on the ground. Next, you are gliding back to the ground, and pressure again, outside pressure and inside pressure again equal. So do imagine fuselage in flight. It's like permanently breathing. It's increased in size due to excess of inner pressure, which correspond to the ground, and reduce it in size when it come back to the airport. And year by year, flight by flight, increase it, reduce it, increase it, reduce it. What happened to the wing and to stabilizer or to massive elements like landing gears? You also have seen on your own. When they are bended and traveled in different directions, like twisting, bending all together, whether flutter or buffing or shimmy, you've seen it. They are not stiff enough. Why we don't do it more stiff? Once again, more stiff structure, typically it's resulted in more heavy structure. More heavy structure, more fuel. More fuel, you need to make again more heavy structure. No, this circle that we are walking on, I have already shown you. Да? I took it, I have not invented it. I took this illustration from one of a book about design that I have already sent to you. It's like closed circle, really. Trying to do it better, it's resulted in worse. And we keep balance between stiffness of structure, thickness of structure, and strength of structure. But if cyclic loads applied, it's a period. We didn't understand it since beginning. I mean humanity, engineers. And I should say, maybe I already said it, not true, not remember really, that history of aviation is written by blood. It's written by blood of pilots, written by blood of passenger. You understand? Even by blood of engineers, because some engineers they used to take part in test flights, and creators of these airplanes, designers, and some phenomena we didn't understand until we meet them, until it's occurred sometimes, like in front of our nose, let's say, including these fatigue phenomena, which been studied really only people start studying concentration of stresses that now you study, like a general information at all. It's something well understood for everyone. Effect of stress is concentration in the places where you have cut-offs, cutouts, holes, openings. Uh, you know it. It was started to be studied in 50th years of previous century, after I mean people as a whole, after we lost some passenger airplanes in transatlantic flights. Effect phenomena of fatigue stresses affecting the structure. It was closely studied. It was noticed and closely studied only since 17 years of previous century. It means not more than 50 years, when people already understand that this phenomena exist and how it's work, and it's still under the studying. The cyclic loads, they are resulted in appearing of micro cracks, and these micro cracks appeared in different places. If you don't notice them, how you may notice it inside of airplane? It's not visible, it's not outside, and it's micro crack. And these micro cracks, they are growing and increasing in size, and in some moment, just piece of structure is broken, and under the load this piece of structure is broken, it does not work. It means that overloading goes to another elements, these another elements also may be spoiled, and so on and so forth. So fatigue matters, fatigue considerations, both in design and in manufacturing, they are extremely important, because they may be resulted in crucial sequences, in critical sequences, in catastrophic sequences. People, I don't mean to scare you after my stories about aircraft design, aircraft manufacturing, you may be afraid to fly after. No, to be truth, to be frank, when I was a child, teenager, I've been flying and I enjoying this process, sitting in passenger cabin. When I start studying in HAI, I already start thinking, should I fly next time or not? But after some after some short period, it's disappeared. These fears or these idiotic ideas. So whatever you listen to from me, don't be afraid that airplane may crack immediately in the air. Thousands of engineers usually working before any particular piece of aircraft technology, aerospace technology, goes to the operating, to the maintenance. Thousands of people are working to study different phenomena, to study design, to test it, and so on and so forth. So I should say that airplanes, and especially because they are operated by very experienced and prepared people like pilots, and because airplane usually, no, as I already said, you stand by it and resolve it, everything in the airplane, including the pilot. Airplanes are much more safe than, do forgive me, bicycles or automobiles that you use somewhere in street traffic every day. They are not so closely studied, however well they are. They are not so closely checked, let's say, however well they are. And the worse, they operate not by the best operators, you understand, that? Because in street traffic, everyone may take part after short training, but not everyone may be permitted to use airplane, and especially when it comes about passenger or cargo giants, or passenger airplanes at all. But do remember what did I say? Fatigue matters. On one hand, they may be solved how, by which way you may increase the weight of structure. No, you may increase the thicknesses of material, the massiveness of structure, and due to this, you reduce stresses because loads seems like the same, quite true in case of airplane. Loads practical is the same, but structure is more heavy, not the way. You do remember, we are working according to the principle of mass. So there are another ways should be to solve fatigue problems, and those who study design, they will study it on higher years and higher courses, let's say in university. But I need you to understand that these fatigue matters, they may be affected to the better or to the worse. They may be affected by choosing of that or another technology. And this idea that structure of forged part repeat the outer surfaces usually somehow of this part, uh, or it's follow to the shape of the part somehow. This fact is resulted next in improved fatigue resistance of such a part being made of the same material, I mean chemical composition, this one and that one, which passed the forging process. Forged one, preliminary forged, next it's also machined by some surfaces. But this one in general, the forged one, will have higher fatigue resistance than that one which was completely cut from plate. Sorry for this deviation. I hope it was useful for you. Let me to see the time. Let me to compare it with what I written. Okay, literally couple of seconds and I will stop, and I will continue about sheet metal stamping in next class after interrupting of these records. No, here is useful information that will stay here in lecture, at least in the screen. You see different temperatures for melting points of different materials. What does it mean in terms of hot stamping or hot for stamp? No, stamping, sheet metal stamping also may be in hot state. It's rather a rare variant, but we use it time to time. Hot forging. Hot forging temperature and melting temperature, it's not the same. For different materials, the most general rule that range of temperatures for hot forging is in a range of 0.5, 0.7 of melting temperature for different metals. Why so no big range for different metals? Because different metals, they have different points of starting of inner transformation, so-called growing recrystallization, grains recrystallization with growing of grains. And this changing of inner structure just due to applying the temperature, it's not desirable, let's say, no, especially in terms in terms of what I have explained to you about fatigue stresses, for instance, about fatigue life of the part. And that is why we need to heat up the part to make it warm, hot, but not to overcross the point where part start self-changing of inner structure due to the temperature. It's not melted, but it's already start changing the inner structure. And these changes of inner structure next, they are resulted in the changing of mechanical properties we are sincerely interested in. Oh, very well. Here is, you see, forging press and fried eggs, as I said you already once. Yes, more probably by the word, no, it's not defective one, it's deliberately made like this. The splitting plane, it's not complete, it's not compulsory a plane, as you might see in this example. The part, the die splitting plane may be staggered. It may be in some planes and with transformation from one plane to another. But whatsoever, what we will see, what are typical elements of any forged part of forgings. Compulsory, no, until it's not cut, you will see here this skirt, as I call, no? It's called flash correctly in English. Compulsory, you will see draft angles. For casting, you also have draft angles, but they are not so significant. When for casting, draft angle like 1, 2, 3 degree. For forging, typically no less than 5. 5, 7, and it will be different in outer and inner surfaces. Don't ask me why right now. Just do remember this, and when you study those bulk processes separately, you may ask another lecturer. And fillets, much greater than necessary for the final part. All these show us that this part was produced by forging. What, as we already talking about this, jump, is it here or not? Yep, it's here. Look at this. No, that one. It's there are slides about already aircraft manufacturing. So some things more close to aircraft manufacturing, and they are ordered in according to technological system of aircraft manufacturing. A bit another order here will be. So what do you see here? I trust you recognize it. There are blades either of turbine or compressor of engine, or turbojet engine, or turbofan engine, and these blades of complex shape of hard meltable material. And what is hard meltable with high temperature of melting? Because it's work in hard condition. You do remember, it's work in explosion, practically in the area of explosion. Of course, it's made of hard processable material, and these hard processable materials of complex shape, if we try to cut those things immediately. No, about fatigue strands you already heard, long and hot story. If even to cut such material, it's too much, it's very expensive and long. And how they are really produced? Is it possible to produce it by stamping? Because of this complex shape, it's not just airfoil, but it's airfoil with twist along the blade. They are not producible by stamping, but they are produced by casting. How, you might say? You said that casting is not appropriate for aircraft manufacturing. Well, yes, I meant that we do not use it in making the airframe of aircraft. But there are special techniques of casting with so-called directed recrystallization, with additional pressure application, which are effectively used exactly for elements of engines. It's casting process, and that is by the word, it's also made by casting. It's not to airplanes, not referred to airplanes, but it's also made by casting. Such complex things better made by casting, because stamping of such thin elements, no, unbearable. It's not possible. And here is a stamping. Part looks more bulk with respect to what we have seen. No, it's more massive. Well, more primitive shapes. No, if we compare it with twisted blades, here you see unprocessed one after the casting. On the left, on the bottom, you see processed one. And what else? I hold on purpose the left side and right side. Do pay attention here. Do pay attention here. That is, by the word, element of landing gear. It's very big thing, actually. No, we see it on the floor, and in order to give you idea about these piles that on the floor, they approximately the size is 20 to 20, I should say. So do imagine the size of the part. It's massive element of landing gear, some rotatable elements while retracting the landing gear, and they produce it. They are produced not from aluminium alloys, as you might understand, and those things they produce it by stamping preliminary with further machining, only by some surfaces, not everything. Some elements of this stamped part, they already lasted unprocessed. During all the fused transformations, you do not touch those surfaces, and these qualities have been obtained by stamping. It will be already quality of final part. Do pay attention once again to these places. You see the tracks of this flash. It's already been cut, but still visible. And do pay attention to the thickness of the flash in this place. I said you, usually it comes about something like millimeter or less. But in case it comes about very thick, massive parts, it may be even around centimeter, as you might see. Here is a scheme of stamping to help you with your imagination to understand what it comes about. And this place, this gap clearance is the place where these elements will be locked inside. And now we see also elements of landing gear. To pay attention how to understand what is the way of their by the word. It's a Boeing, but not it's a Boeing. It's produced not at the Boeing place, not at any enterprise that belong to Boeing. It's made of titanium alloys, and it's made not in America or any another place where they have Boeing enterprises. Boeing just purchase it, and do guess where? Titanium alloys. So these things they are produced once again by stamping, and that is visible immediately by these lines that appear as resulting of cutting the flash. And here you see what effect that I've been talking about. You see that it was already partially cut, and you see rough surface finish. It's called surface lay. You see the tracks where either mill, or more probably it was not a mill, it was, no, in this direction at least, it was turning cutter. Tracks left due to their, after the processing. It's not even surface roughness. It's so-called surface lay. The sort of outer texture has appeared due to processing. And effect of different surface roughness. Now you see it's already more processed, but do pay attention, quality of surfaces is different. That one is more glancing, that is less like muted one. But it's already processed, and maybe processed finally after stamping. Where surface roughness is higher, of course, where it's more polishing, where it's glancing, that is surface roughness. No, whatsoever, what I meant to show you that by some elements in some structural elements, not structural elements, by some features, let's say, in the pieces, in semi-products, it's easy to understand how they been produced. And we will stop on this and continue about sheet metal stamping in our next class. Once again, remind you, open die forging, closed die forging, the differences between them. Open die forging, metal is not locked inside the die, and at least it has one way to exit, at least one, maybe in two directions, and fulfill it with more primitive tools. Closed die forging, fulfill it in, it's not me, it's my helper. Closed die forging, it's fulfilled with help of special tool, die, which lock material inside completely. And due to this fact, we have inner changing of structure that we're interested in. And also there is misunderstanding in terminology. In our country, we call it, as I said, volume stamping, and we have also the group of processes inside of this volume stamping, which is called closed die forging. In English, the same things, that we understand as closet die forging, if it directly translated to English. They are called flashless forging. They also have this group of processes, practically enclosed die, really, as you might see right now, but it's called flashless forging. What that is really closed die, because practically no flash at all. No, quite clear that this process is more complicated with respect to the conventional closed die forging, but somehow it's more useful, more profitable. Yeah, about this we have finished, and the same thing you see, and or practically the same things. And we will continue after interruption. We will continue about sheet metal stamping, about soft skin transformations.